Hello everyone and welcome to the session 5 of NPTEL course in pharmacognosy and phytochemistry. This week we are particularly learning computational and database and as well as web-based server techniques which can help understand pharmacognosy and phytochemistry much in detail. So far with the previous sessions, we already have studied plant-based databases. We already have studied databases pertaining to the traditional applicability as well as ethnomedicinal plants. This included, if you remember, your TKDL, IMP-PAT as well as Indian Medicinal Plants database. Thereafter, we went in to study what are called as the phytochemical search. So, once you kind of shortlisted the plants, these are the softwares which can help us in letting us know what all phytoconstituents these plants contain. Then in the fourth session, we went in to understand a little bit more about the phytochemical properties. Now, once you did the phytochemical properties, it was through your PubChem, Lotus, Zinc natural products, wherein all the properties, especially the physicochemical properties of your phytochemicals were found out. We also saw the natural product likeness of the compounds. In the last session, what we learned was what or how can we know whatever we have purified is actually a real compound that we are looking for. Is it the same one or is it anything different basis the spectroscopic analysis, and this all spectroscopic techniques gave us some values to compare with. Now in today's session we will move a step ahead and we will see what are the databases that can help us predict the pharmacokinetic as well as pharmacodynamic properties. Now, there are certain softwares which are paid, say for example GastroPlus or Simulation Plus. They are indeed a good softwares, but those kind of require some initial registration as well as fees. So, in this session I will be particularly focusing on the freewares that we all can use and still get an idea about the ADME, that is the pharmacokinetic as well as the pharmacological properties or the therapeutic properties of your phytoconstituents. So, here are few softwares that help us. One is the Swiss ADME and also there is what is called as Swiss target prediction. Swiss ADME is more about pharmacokinetic, whereas Swiss target prediction is more about the pharmacodynamic effects, which will tell us that what would possibly be the effects of consuming this drug. Not only that, you have few other softwares such as PKPD AI, which also gives you the pharmacokinetic properties. You have Oshadi databases, we have C server, which is a similarity based server that is going to help us determine the activity as well as the therapeutic target database. So, let us see them one by one and analyze what each of them have to offer. So, starting with the Swiss ADME database. Swiss ADME database is a database which kind of predicts the pharmacokinetic properties. Now, here are two ways in which you can enter in your query. You can put in the 2D format, what is called as SMILES, or you can draw the structure. So, if you want to draw the structure here, again let us go to our same query so that we know what each software can offer us. We will go to our query and that is our quercetin. Just kind of replacing this all by O. So, here is our quercetin. Now, if I just click on this, this will convert a 3D structure into a 2D format. It is very simple, it is what is called as the SMILES format. So, you can see here this is what is called as the SMILES notation. You can use this for predicting the properties. So, I am just copying. Now, once you have this been predicted, I will just click run. Now, it is kind of calculating and you can see a loading signal. Once that is done, you see a few properties. Now once what is called as, this is the spider chart, and the spider chart will tell you it is a possibility of druggability. Now for druggability, you see a little inner pink region. The properties such as flexibility, lipophilicity, size, polarity, insolubility and insaturation should be all within certain limits. Now what does this indicate? This indicates that the lipophilicity is optimum, the size is optimum, polarity is optimum, so is insolubility. The unsaturation can be little less. The flexibility can be even little more is permitted, but it is almost going to a perfect region. So then going down, you can see certain things such as the molecular properties. We also saw them in your other databases which gave the physicochemical properties. This includes your molecular formula, molecular weight, heavy atoms, number of rotatable bonds, hydrogen bond donors, acceptors and total molar surface area. The next gives you an idea about the lipophilicity. So comparatively these readings are low, that means this molecule is less lipophilic. Now here this next parameter is your water solubility, wherein it is almost water soluble, that is moderately soluble. Then GI absorption is high and blood brain permeability is no. What does that mean? That means it's definitely when you're consuming it, you need not give it additional formulation ways or treatments to increase its GI absorption, because naturally its GI absorption is good. But if at all you have to make this drug or make this molecule reach your brain, what is going to happen here? The blood brain permeability is 0. So in that case you will require specific drug delivery systems to make or to deliver this molecule across your brain. So you have in your liver what are called as cytochromes. So these cytochromes are very vital for the normal metabolism to happen. So is consuming your drug kind of, now in this case there is no oxygen, so I cannot call it quercetin, but let us call it drug. So is this drug going to inhibit any of this cytochrome? So if the answer is no, what does that means? Whatever drugs are getting metabolized by this particular molecule, there will be no effect. But if you see this last, that is CYP3A4, that is CYP3A4. So CYP3A4 is also a active enzyme which is involved in metabolism of lot of drugs. Now if this is an inhibitor, what does that mean? This is going to inhibit this enzyme. If it is inhibiting this enzyme, so whatever naturally the drugs were getting kind of metabolized by this enzyme will not happen. And you also have skin permeability values. You have your drug likeness. So there are certain values we follow that for a drug or for druggability. You have your Lipinski's rule of 5, that is the molecular weight should not be more than 500, and a lot of other rules are there, and depending upon the scientist and their rules, the software is automatically calculating how many hydrogen bond donors are there, how many hydrogen bond acceptors are there, what is the molecular weight, what is the molecular size, what is the molecular total polar surface area. Based on these rules, it is trying to fit in these rules and it is saying that is it compliant or not. So it is mostly compliant, so there is a good chance that this is a druggable moiety. So pains are kind of false alert, so yes, one alert is there and that's catechol. So in terms of medicinal chemistry you need to do this, and definitely it is synthetically accessible. Okay. Now I will just modify this to a quercetin further, just to see if anything changes. Or what we can do this time is we will just clear this off and we will use the values taken from PubChem. You can directly from the PubChem, you remember we saw it in the previous session. So you can just quickly raise a query of quercetin. From that you pick up this region called as the SMILES, which is essentially the 2D format. So what I am doing now is I am just copying this. I am putting it in my Swiss ADME, pasting it here. So I have my quercetin as a query now, and then I hit on run. So you can see here It's kind of running the query, and this time it is coming with oxygen. So yes, little bit of parameters have changed. If you see here, now this molecule is also a CYP1A2 inhibitor. Druggability is almost retained and the pains is a catechol. So again the solubility and lipophilicity has changed slightly. If you seen, the values were earlier close to almost 3. So now it is less lipophilic, that is, it is more polar. Now we move on to the next one, and that is your PKPD AI. Now PKPD AI is not a structural based database, so it is not predicting based on calculation, but it is predicting based on searches. So what I can do is a quick literature search for my molecule. So if I have to do PKPD literature search, I will enter in through this website. So again I will do my quercetin search and see what is happening. So ideally earlier ones gave you properties based on calculation, this ones will give you or come back with the articles. So you can see here the effect of quercetin on cytochromes, on P glycoproteins, effect the effect of quercetin on pharmacokinetics of other drugs including. So all of these articles which you are seeing will be based on pharmacokinetics of your quercetin. So if you want to do a literature on PKPD properties of any molecule, you will search it through this particular software. Now moving on to the next one is the Oshadi software, which you already seen. This time we will go in the last tab, and that is your cheminformatics. Again we will try to search. Let's click on the first molecule herein. So here Oshadi software comes or tells you about again the cheminformatics, or it tells us about the chemoinformatics of a molecule in terms of its heavy atoms, rotatable bonds, hydrogen bond donors, aromaticity, solubility, saturation. So you have your natural product likeness score, which is very high, more than 1. Then like I said, there are a lot of rules which are pertaining to driggability. So you have Lipinski, which is accepted, the ones which are set in by Pfizer or GSK are rejected, golden triangle rule is accepted. Absorption, P glycoproteins, no. Kako, yes, but minimally it is on the negative side. You have certain cell lines which are reported. If you see here, the blood brain barrier score is very less of this particular molecule, but yes, it is permeable. Then how much it is able to, there you just got yes, no as an answer if you recollect in your in your Swiss ADME database. But even in your PKPD AI you can see the literature. Here it will more bring you curated values of cytochromes action or metabolism. This is kind of a clearance values, toxicity values. So you can see here you get a good data. So is it antiviral? No. So Oshadi kind of database gives you readings about the physical attributes, chemical attributes, the drug likeness, absorption, distribution, metabolism as well as excretion. Now we move on to more of pharmacodynamic databases. Now pharmacodynamic databases, so far what we saw is what will happen to the drug in body. So once you consume it, is it going to get digested by your cytochromes? What are going to happen to it? Now how will or what will be the action of this molecule on our body? So for this we will first move to what is called as Swiss target database. This is the same software wherein we saw the Swiss ADME, but this software or this particular web browser kind of helps us in bringing out what is called as the pharmacodynamic properties. So again I am just quickly deleting this and I am pasting my query, which is quercetin. So I pick up my SMILES again and put it here so that we do not make any mistake. So this, you can see here, it has got the quercetin structure. Now I am asking this software to predict target for me. So when we put in the query of quercetin in the Swiss target database, here you can see the browser returns with certain results, and if you see it carefully, you can see it in terms of enzymes. That is, thus enzymes are demarcated by different colorations, and you would see lyase, kinases, oxidoreductases and so on. Now many of these enzymes have been involved in disease condition, and as a result, if you see carefully, the software gives you exactly that. So you will see that it is involved actively in interacting with NADPH4 oxidase, aldoreductase, cyclin dependent kinase, xanthine dehydrogenase and so on. So wherever this disease involve this kind of enzymes, the interactions, because it is interacting with quercetin, there is a good possibility that this drug, especially a quercetin, will interact with this enzyme and bring about the pharmacodynamic. So you can see about 100 such interactions with different enzymes have been brought in. The limitation of this is you can definitely predict the interaction, but the intensity or the dose or the amount of interaction cannot be seen herein. Now going to here, that is the next database, that is your therapeutic target database. Here you put in your drug, say for example quercetin again, and then put on search. So you can see quercetin, it is approved for obesity, and this is the TTD ID. So again it is phase 2-3. Basically what is here is a quercetin glycoside, what is called as contigoside B, and it is almost reach a phase 2-3. It's used for thrombosis. Another, what is the methyl ester of quercetin, is again investigative and the mechanism is unclear. You will see numerous derivatives of quercetin which are under investigative research. So rutin, quercetin neohesperoside. So it will come across different things. Now just let's click on the first one and see the information. You can see here, this is all the names it is, or synonymous it is known with. This is the target PCAT, and these are the references or literature from which the web-based server has kind of predicted that it may show a kind of activity, especially as a hypoglycemic or as an anti-obesity agent. Now we move on to the last one, and that is a C-based server. Now C-based server is what is called as a similarity ensemble based approach. So what this server does is it kind of curates a list of molecules. So say for example, based on the structure, not only based on the structure, based on the structural similarity. So it will pick up a pharmacophore, and basis that pharmacophore, it will tell you what all activity it has. So say for example, I am putting a query of quercetin again. Again I will just pick up canonical smiles or smiles. I put it in my server and I paste it. So what does it tell you now? So it can tell you that this molecule, which is your query, that is quercetin, is active against all of these genes which are there, or you can even call it different receptors which are there. Now these receptors may be human based, mouse based, you can have it rat based and so on. So it's very non-specific. Then you have a typical abbreviation or target name and the description of the target, where exactly this is found to be active. Then you have what are called as p-values. These are statistical value which tell us how much relevant or how much statistically significant is the activity. A value less than 0.05 is considered to be a good p-value. The last table gives you what is called as the Tanimoto coefficient. Now what is this Tanimoto coefficient means? The TC means the structural similarity. So if the TC value is 1, that means the structural similarity is 100% and this activity is of quercetin itself. But as you move down the table, you will see that the TC values might go on decreasing. You can see here the values are less. Now these values are less, the reason being the Tanimoto coefficient, the structure is not matching. Maybe now imagine a molecule which does not have these two hydroxys. That means the percent similarity to quercetin will decrease. So how much percent similarity decrease? If you consider 1 as 100, now this is almost 76% structurally similar to quercetin. Whereas this is something, this is a molecule which is 60% structurally similar. So something that is not 1, it has highlighted in other colors, so it will be easy for us to demarcate that this is not quercetin, these are other molecules which have a good structural similarity to that. Now imagine this has just kind of 39% structural similarity. So in that case, where the structural similarity goes below 70%, it is recommended that you do not pick up these values, because less than 70% similar may indicate that it will no longer be a flavonoid nucleus. So today we saw different databases, the Swiss ADME databases, the PKPD AI database, the Oshadi database, the C server, TTD database, as well as the Swiss prediction database. Some of these databases give us pharmacokinetic data like your Swiss ADME, PKPD as well as Oshadi, whereas some of them also gave us the dynamic data which included the TTD as well as C server as well as your Swiss target prediction database. So with this we end our course in pharmacognosy and phytochemistry. Through this course we have been able to kind of learn what is pharmacognosy, what is phytochemistry, understand different classes of compounds, understand their methods of analysis as well as quality control, and with this session we are also able to predict and compare computationally what spectral, what physicochemical as well as what are the pharmacological properties of this. So thank you everyone for being an avid learner. At the end of this course, I would like to acknowledge my institute, the Institute of Chemical Technology, Mumbai, for this stupendous opportunity of collaborating with NPTEL, my TAs Megha and Akansha, who have been very supportive in this role, as well as our laboratory staff, Mr. Kiran and Pooja Patil, who have been helping us with the experiments. I would also profusely extend my heartfelt thanks to the NPTEL IIT Mumbai team, without which this would not have been a possible thing. So thank you everyone, great learning, and wish you all the best for your examinations. Thank you.